Hi, so this little video to try and help both Year 9 and Year 10 with your revision for your mocks. So for Year 10, this is if you are not in school this week and you should be watching this instead of your lessons. Year 9, obviously none of you are in school, so this should be for the higher sets only. You should be watching this to help with your mocks revision. Right, we'll get straight on with it. So we're jumping straight in. This is all about electricity, and we're going to go straight in with the circuit symbols. So got two basic ones here that you should remember: lamps and switches. Lamps, sometimes called a bulb. Switches we know can be open or closed, but even if you have an open switch, it's not a break in the circuit. It's not like there's nothing wrong. Often you'd have a switch in there and people would pick that out as something being wrong with the circuit. It's just there, and obviously you could close it. Okay, it does work. Moving on, cells and batteries. So we've got a cell and a battery here. Okay, our cell is just one and our battery is more than one. If we take our cell and we double it up, it becomes a battery. But when we have a battery, generally, you put a dotted line in the middle to show that it's a lot of cells. Okay. Now, other thing you need to note with this is that there is a positive and a negative side, and the current always flows from positive to negative. So it goes out of that way, round the circuit round here, and back into the negative side. So we need to make sure that we always put them going the same way, so that they're all both these two cells are pushing the current round the same direction. Okay, they're both trying to push the current out this way. If that didn't happen, if you sort of drew this wrong, which a lot of people do, or you often get given it wrong in an exam question and asked like what is wrong with it, then in this case both of these would be trying to push the current the opposite way, and that would just not work. Okay, that there would be nothing happening because they're both trying to push the current the opposite way. It just gets stuck, nothing would happen, and you just would get a circuit that just wouldn't work. So really be careful that you make sure your cells are facing the same way when you draw your battery. Right, moving on to two other ones that we should know. We've got our ammeter and our voltmeter. Now, I'll put in underneath these series and parallel because that's where they should go. So our ammeter should go in the main circuit in series because it's measuring the current through the circuit. And the voltmeter should go in parallel because it's measuring the potential difference across a component in the circuit or across a certain section of the circuit. So it's got to go in parallel to measure across. Right, next one we've got, let's change that. So this is a fixed resistor. So a fixed resistor, just a rectangle with two lines coming out of it, and that shows we've got a resistance which is constant. Okay, it's a set resistance which doesn't change. So it might be 10 ohms and that's it. It's 10 ohms of resistance. We can change this though to various other things. I'm going to keep changing this. The next one I'm going to draw is a variable resistor. And a variable resistor is one that can change the resistance, and it looks like this. You put an arrow through it like that. So you've got to get these exactly right because they're very similar. Okay, we can see that without the arrow, fixed resistor, with the arrow, variable resistor. So variable resistor allows us to change the potential difference in the circuit. So it allows us to share out the potential difference in different ways, and it can allow us to change things in the circuit and get different readings. Now, another one that looks very, very similar to this, next I'll do is the thermistor. I didn't just do it the whole thing. So a thermistor looks very similar to one with the variable resistor, but this time we have a line going parallel along the bottom for a little bit, then it stops and it goes up like that. Now, your thermistor is one which changes based on the temperature. Okay, so it changes its resistance based on the temperature of things around it. And basically, as the temperature increases, the resistance of the thermistor decreases, so you get lower resistance. And this is used in lots of things. This is used in things like thermostats that turn your heating on and off instantly, used in ovens, so when it gets to the right temperature, it stops getting any hotter. Used as a safety device in things like hair dryers and hair straighteners, so if it does get too hot, it switches it off. Right, next one, similar to a thermistor, is an LDR, or a light dependent resistor. Okay, so LDR, light dependent resistor. Now, light dependent resistor, similar to a thermistor, changes its values based on something. Well, this time it's based on light. Okay, so in this case, we draw our resistor, we draw a circle around it, and we draw two little arrows that represent light going into it. And this shows us that the light affects the resistance. And in this case, the more light there is, the less resistance there is. So more light, less resistance. Now, this is really useful in things like automatic street lamps, automatic car headlights, things like that. So things that you want to come on when it gets dark, okay? And allows you to turn on by itself and doesn't have to have someone going around switching them all on. Right, moving on. So, next one we're going to look at, which again has a couple of different variations, much less this time, is our diode. Okay, so this is a standard diode, and this only lets current go through in one direction. So the current can go through in this direction here. Okay, it's like a funnel. So if the current's flowing through this way, absolutely fine, it can go through. Okay, but if the current tries to go through the other way, it's blocked because it's got a very high resistance in this direction. So it can go through this way, so that's okay, but it can't go through that way. It cannot go through that way. So if you get this, often you're given a drawing of a diode like this, and you're asked, will this circuit work? So if it looks like the current's going through this way, then yeah, it's going to work. If it looks like it's going through this way, it's not going to work. Okay. So the other type of diode we've got is an LED. So that is a light emitting diode. So a light emitting diode, similar to looks a bit similar to an LDR in a way, because you've got the arrows coming on, but be careful with this because it's emitting, it means it's giving out, so the light is given out from it. So this is the same as a diode, does the same thing with the only letting it go through in one direction, but this time it gives out light. Okay, so that is all of our circuit symbols. I don't think I've missed any. No. So they're all there if you want to see them all. And just a little bit of an explanation as to how they all work. So we're going to move on now to looking at some of our sort of keywords that we've got. Okay, so first off, we're looking at potential difference. It's a really confusing concept, potential difference. If you want in a definition, it's this at the top here, so I'll highlight that for you actually. So potential difference is the energy needed to move one unit of charge between 2 points in a circuit. If you write that, you'll get your answer for writing a definition. Okay, so in terms of just knowing the definition, that is it. But trying to explain it's a little bit more difficult. So basically, what happens is, I always imagine it like lifting something up and it falling back down again. So imagine this with water. What the battery does is pump the water up from the bottom up to the top. So we give it more energy. Okay, so imagine like electrical energy, but it's hard to see electrical energy, it's hard to visualize it, but imagine it like gravitational energy. So in the battery, what you're doing is lifting up the energy level. Okay, so you're giving it more energy. So when your current comes in through into the battery, electrons go in, you give them lots of energy. And as they go around the circuit and as they go through a component, they lose the energy like it's shown here. So when it goes through the bulb, the energy is lost. And that's why we need the voltmeter to go in parallel. Okay, so we measure potential difference in volts using a voltmeter, and it needs to go in parallel because we need to know what is the difference in energy between here and here. Okay, we need to know how much energy is it lost as it goes through the lamp. So like this here, this middle bit, that is our lamp in this case. Okay, so as it goes through the lamp, it's losing energy, and we need to know how much energy is it lost from there down to there. So we need to attach our voltmeter across from one side to the other. If you just put it, you put your voltmeter like here, okay, it's not going to work because there's no energy lost in that bit because it's just a bit of wire. So that's why we need to do that. So moving on, current is the rate of flow of charge. That their rate of really important. That means how much charge is flown per second. So it's not the speed that it flows around. That's not quite right. Imagine like a little stream. Okay, the water might be flowing really fast. Might have a really fast flowing water in a little stream going down a mountain. But a big river is going to have more water. It's going to have a higher current because more water is flowing down it. Even though it's not as fast, there's just more of it. So it's not quite about speed. It's the rate of. Okay, so how much per second. So the rate of flow of charge, or it's how much charge flows through a circuit in a second. Okay, so if we look on here, we can see the little electrons flowing around. Okay, our charge flowing around, our current flowing around through our wire. And if we put, and going back to the like water analogy, if you put a little water wheel in here, okay, you might be able to see like how much water is going past in a second. And we'd have to put that in the main circuit somewhere, in the main current. So we put the ammeter to measure the current in the main circuit, okay? So it goes in series. Right, so important things, current is the rate of flow of charge or how much charge flows per second. Either of those bits would get you marks for your definition. We put our ammeter in our main circuit in series, okay? So it can measure, it can like count almost how much charge is going past every second. Charge, by the way, just being like the electrons flowing around. Right, moving on to resistance. So resistance, again, definition here, is the property of material to resist the flow of charge around a circuit. So it basically tries to get in the way, tries to stop the electrons, the charge flowing around the circuit. So imagine inside a wire, if you will. So in year 10, you'll have done this last week because you did like metallic bonding. So you should know we've got delocalized electrons and metal ions. And your delocalized electrons are being pushed around the circuit by your battery or your cell or whatever. So these are flowing along, and you can see some of them are just going to flow through no trouble at all, but some of them are about to hit our positive ions or even go near them, because if you remember, electrons have a negative charge. So if that negative charge comes into contact with this positive charge, so if we just zoom in on that a little bit, so yeah, if we just focus on these two, so we've got one that's going to go near it and one that's going to hit it. Both of these are going to be deflected, and those collisions cause resistance. So the more positive ions there are, okay, so imagine if you stretch this out further, so if I double the size of this, there's more ions, there's more chance of them colliding, so there'll be more resistance. So the longer wire gives you more resistance. Also, if I try and squash this up, so if I took that top layer out, okay, so if I covered that up, took that top layer away, yes, there's less electrons, but there's a lot less space for them to move through now. So it's much harder for them to get through. So I've squashed this up and it's much harder for the electrons to get through. So a thinner wire would also give me more resistance. Now, we measure resistance in ohms, okay, and the funny little symbol there, the omega symbol, that represents ohms. Now, we don't usually measure resistance directly, okay, there are things that can do that, but we won't use them in school and you don't use them in GCSE. But you can work it out. So what we need to do is measure the potential difference in the current and use this equation. Potential difference equals current times resistance. So if we use that equation, we can work out the resistance by calculating it, okay? Right, moving on now. So we're going to have a look at those equations. So first equation we just talked about, potential difference equals current times resistance, with potential difference in volts, current in amps, resistance in ohms. And our second equation we need to learn for now is charge equals current times time, with charge measured in coulombs, current measured in seconds, time measured in amps. So working one of these out. So we've got a circuit with a current of 6 amps flowing through it for 2 minutes. How much charge has flown through in this time? So let's go back to our equations. Right, so we've got here, it's given us the current, it's given us 2 minutes, which is time, and it's asking how much charge. So we want charge, time, current. Which one's got charge, time, and current in? It's this one here. Okay, so we're going to charge equals current times time. So I'll copy that over actually. Right, now, got a problem though. Look back at this again. We want charge in coulombs, that's the answer we're working out. Current needs to be in amps, got them the wrong way around. And time needs to be in seconds. Now, our current is in amps, brilliant, we can just use that. But our time is not, our time is in minutes. So I need to convert that. So I'm going to do, to work that out, 2 minutes times 60, because there's 60 seconds in a minute, equals, and that's 120 seconds. Okay, so when I put that into my equation, that's what I'm going to do. So my next line of my equation is going to look like charge equals my current, which is 6, times my time in seconds, which is 120. Okay, and then I can just work that straight out. So my charge equals, so 6 times 120 equals 720. And I'm going to put a capital C on the end for coulombs, because that's the unit that I'm going to use. So I've got my answer there, 720 coulombs, worked out like that. Right, next one. So this time I'm given a picture, not an actual worded equation. And it wants me to measure the resistance. And I've got next to my voltmeter, I've got 6 volts, and next to my ammeter, I've got 1.5 amps. So I want to find resistance, and I'm given a current, because it's my ammeter, which measures current, and a potential difference, because my voltmeter measures potential difference. So again, which equation am I going to use? It's going to be this top one, isn't it? Okay, potential difference equals current times resistance. So if I was to put that at the bottom and make the page bigger. So this time, right, remembering I need my potential difference in volts, current in amps, resistance in ohms. So my potential difference is in volts, excellent, and my current is in amps, even better, so I don't need to do any converting. So all I need to do, put my numbers in. So I'm not going to try and, some of you might notice, right, this isn't the right way around at the minute, but I'm not going to try and rearrange yet, and you shouldn't be doing that. So I'm just going to put in numbers in underneath where they should go. So I'm going to do 6 volts equals, my current is 1.5 amps times, I'm just going to put R for resistance. So I've got 6 equals 1.5 times R. Get rid of the amps and the volts, make it a bit simpler. So what have I done? I've done 1.5 times R equals 6. So how do I get just R on its own? So I'll work out, right, what did I do to R to make 6? So I did 1.5 times it. So if I do the opposite, I should just get R on its own. So if I do R equals 6 divided by 1.5, I should get my answer. Okay, so if I do 6 divided by 1.5, I get 4. So R equals 4, and it's ohms. You see, if you're writing this, you might want to write the symbol in, but it's not on my keyboard. So 4 ohms. Okay. Right, moving on to series circuits and parallel circuits. So a couple of rules you need to remember. So these are basic ones, and there's a few more things to remember on top of that. But first off, the current is the same in all places in a circuit. This is for series circuits, sorry. So in a series circuit, current's always the same. So if you look, the current at one side is 0.5 amps, the other side is 0.5 amps. That's because if you think about what current was, it's the flow of charge around the circuit, or the rate of flow of charge, and it's not changing anywhere. Okay, there's the same charge flowing all the way around. Okay, like the electrons are all flowing around together. It's not like one starts and has to go all the way around. As soon as you push on one, imagine them like marbles in a tube. If you've had a tube filled end to end with marbles, if you push one marble in there, then all the marbles start moving at the same speed. So all the electrons move around at the same pace all the way around, because there's nowhere the circuit's broken up, it just goes on in one continuous circuit. The potential difference is divided between the components. So if we look, we've got 12 volts from our cell. Okay, so 12 volt cell is split into 6 volts and 6 volts. Now that's because we've got equal resistance. Now that's not always the case. If you, for some reason, say if I had different resistors, in fact I'll just change them on here. Say if one of them was 6 ohms, and one was 12. Okay, because one's twice as much as the other, the one with twice as much resistance will get twice as much potential difference. So in this case, this one would get 8 volts and this one would get 4, because we've still got to share the 12 out, but we've got to share it out equally. And you quite often get a question where you might get something like, you might get, right, so we've got a 12 volt supply, we've got 8 volts in this one, how much is in this one? And you've got to work out, right, so 12 is split up into 8 and it's got to be 4. Okay, so it just splits up. Now, get rid of all that. Ooh, there we go. Sorry. There we go. Right. Right. That's better. So now looking at resistance. Resistance adds up. So basically, if you have more resistors, you have a higher overall resistance. So 12 ohms add 12 ohms. How much is that going to be? So that's going to be 12 ohms add 12 ohms is 24. Okay. So the 24 ohms total, because we're adding those up. So if we add those together, you're going to get 24. If I added another resistor, it would go up to 36, okay, of the same one. So the more resistors you add, the higher the resistance gets, basically. So remembering these rules will really, really help you, okay, in terms of then just working things out. Because if you were asked, like, what is the resistance at this ammeter? You can work out, well, this has got to be the same, it's 0.5. If it said these two voltmeters are equal, what is the potential difference? Sorry, these two resistors are equal, what is the potential difference? Right, 12's got to split up equally, it's going to be 6 and 6. What is the total resistance? 12 add 12 is 24. Easy to do if you remember the rules. There's no difficult maths, nothing hard. It's just remembering the rules and using them, applying them properly. Okay, so when you get a question on series and parallel circuits, they often look really hard and it's really off-putting when you see it. But if you just think about, like, right, what rules do I know? And just list them in your head. You need to, like, have these imprinted onto your brain so that when you come to your exam, it's easy. You just go, right, oh, it's asking about current, it's a series circuit, current's always the same, it's got to be 0.5. It's asking about potential difference, it's a series circuit, it splits up equally because they're the same. There we go, easy. Right, moving on to parallel circuits then. So in a parallel circuit, the current splits up between the branches. So again, I've done this in an equal way, but it's not always equal, and I'll go through that in a minute. So in this case, 0.4 amps splits up into 0.2 and 0.2 because there's two branches. So imagine again, we've got, like, come back to what we talked about water before. Water's flowing down here, half of it goes that way, half goes that way, because they're equal sized pipes that they're going through. But if I made one of the pipes thinner, it might not be as easy to get through. So if I said A had a higher resistance, it might only let through 0.1 amps. And if we knew there was 0.4 total, we could work out, right, this one's got to be 0.3 then to make that total at the top the same. So it depends totally on the resistance of the resistors. Basically, the higher the resistance, this is true all the time, the higher the resistance, the less current goes through. The lower the resistance, the more current goes through. Okay. Now, potential difference is different in this in parallel circuits. It's always the same across each branch. So if we've got 6 volt cell at the top, then it'll be 6 volts on A, it'll be 6 volts on B. I could add C, D, E, F all the way to Z, and it'd still be 6 volts, as many branches as you have. That's why it's useful sometimes, because you always get the same potential difference across each of your components. So if you have a set of Christmas lights, okay, then by adding things in parallel, you are making things brighter essentially, because every bulb gets 6 volts. Okay, every bulb gets 6 volts, which allows you to get much brighter lights. Also, if I take one of these resistors out, so if I just for some reason just go out and take that resistor out and break in that circuit, okay, the other one would still work. Whereas in a series circuit, if I take one of them out, there's a break in the circuit, it can't work at all and it can't go through the voltmeter. So it's breaking the circuit, it doesn't work, and it's broken. So parallel's good as well, because if one of the components breaks, the rest are fine. Okay. Now, this is the most complicated bit about parallel circuits, the most difficult to understand, but I think it makes perfect sense. resistance gets lower if you add more branches. So essentially, what I'm saying is, if I add another of these down at the bottom, my resistance gets lower. And that seems a little bit counterintuitive. It seems a little bit daft. It's like, well, how you've got you've got more resistors and it gets lower resistance. That's stupid. Okay, but I like to think of it like going to Tesco. Okay, if I go to Tesco and I have got 2 tills open to me, 2 tills available in Tesco, allowing a certain amount of people through. Okay, some might be faster than others, causing less resistance than other ones. Some might be slower. Okay, this is little old Margaret who likes to have a chat with everybody who goes past. Okay, she's chatting to everybody as they go past, so she's really slow. Lovely, but really slow, and she takes ages to serve everyone, but it's still faster with her there because she's still letting some people through. And if we open a third till, we're going to get more people through altogether. So by opening that third till, we've actually increased our total number of current going through to 0.7. Okay, so we add all these up. Again, going back to the Tesco thing, increases the number of people who can get through. So the more resistors you have, the lower the resistance is. So add an extra resistor, get a lower resistance. Okay, next bit, we're looking at potential difference and current graph. So this is based on one of the compulsory practicals that you will have done. So basically what you did was you set up this circuit and you had a power pack going round to an ammeter, and then you put a component in. Now that could be a bulb, or it could be a resistor, a fixed resistor, or it could be a diode, and you swap that out in various times. And what we did was we used this thing here, a variable resistor, to change the potential difference. So we put that in to change the potential difference in the circuit. And basically, like we talked about with the potential difference here, we change the resistance of one of these. That changes how much of a share of the voltage, the potential difference, the other one gets. So by changing the potential difference, changing resistance of this, we alter the potential difference across the component. And that allows us to measure the current. Okay, so we're changing the potential difference, so that's our independent, and we're measuring our dependent is our current. Well, and then we're using this to then plot a graph of our resistance. And if this works perfectly, if this follows Ohm's law, which says that the potential difference should be directly proportional to the resistance, then if we double the potential difference, say we double it from 2 to 4 volts, we should also double the current. Now, with that, with a normal wire or a fixed resistor, this does happen, and we get, I'll split these up, a graph that looks like this. So, let's just take the black line as our original one. We've got, as the potential difference doubles, the current doubles. And if we look in the negative direction as well, because you can have a negative current, which means it's going the opposite way. So basically, all we need to do that is take our power pack and reverse the way it's going. So I could do that by literally taking the battery of the power pack and flipping it round. Okay, or if you were doing this for real life, you'd swap. If you pull your, like you've got your red and your black cable, black holes in your power pack, the positive and negative terminals, take those out, swap them round, and you reverse the current. So reverse the current, and I measure the opposite way as well, and I get the same thing, get it directly proportional. Now, if I did this with a higher resistance, I'd get the blue line, because the blue line shows that the more volts I'm putting in, I'm not actually getting that much more current out. Whereas the red line shows a low resistance, because I don't have to put many volts in to get a really high current. Okay, so basically, the higher the resistance, the less steep the line is. Right, moving on to a filament lamp. Now, based on that higher resistance, less steep the line is, look what happens up at the top. It's starting to get less steep, so that means the resistance must be getting higher. Now that comes back to, where's it gone? Our resistance thing. Now this is because as this starts to get higher, as the resistance starts to get, as this potential difference starts to get higher, our little ions start to vibrate, okay? They start to vibrate because it's getting hot. Because you think about a lamp, it gets hot when it gets really high resistance. And when they're vibrating, it makes it really difficult for the electrons to get through. So they're vibrating around a fixed position more and more and more, and it makes it really hard for the electrons to get through. So we get it being quite proportional in the middle. Okay, so if we take a look at just the middle bit, okay, just have a look at this little look here. Just at a low potential difference, it's proportional. It's directly proportional, it's going up in a straight line. So then when it gets hot towards the end, at the high potential difference, that it starts to curve off because the resistance is getting higher. Right, the last one. We talked about diodes a little bit already. They only let current flow through in one direction. So we'll see that when we reverse the current, when we took the cables out of the power pack, swapped them round and put them in the opposite terminals, swapped the positive and negatives round, nothing happened, okay? In this negative space, there's nothing there. It only allows current to flow through in the positive direction, okay? They've got very high resistance in the negative direction, so they don't allow any current to go through at all. Now, thinking about this then, how can we, which of these has a highest resistance and how can we tell? So the red line, green line and blue line. Now the answer should be the blue line, because as we're increasing the potential difference, say if we take, I don't know, this here is 4 volts. All right, let's have a look. What's the current at 4 volts for this? It's really low. But what about for the red and the green line? So just do that line straight up. So for the green line, we've got much more current, and the red line, we've got much more current. Because resistance, again, remember, is a measure of how much a material tries to stop the flow of charge. So with the same amount of force pushing it, the same amount of energy difference that's pushing the current round from the same potential difference, we're getting much less current able to go through from the blue line, which shows it must have a much higher resistance. Okay, if you are Year 9 watching this, this is where you should be able to finish the rest of your booklet from now. So you should be now prepared for your 8 marks. If you're Year 10, you need to keep watching because there's a couple more bits, not much longer left now, trust me, before you can finish the rest of your booklet. So we're going to have a quick look at a plug. Okay, so a couple of quick things. I'll go through these two at the bottom first because they're the quickest and easiest. So outer insulation, what's that going to be made of? That's going to be made of plastic or rubber. Okay, and that just insulates the wire. Okay, I'm just going to write a couple of important things. I'm not going to write absolutely everything on here. So it's plastic or rubber and it insulates the wire, stops it from electrocuting you. The cable grip stops the cable from being pulled out. So if you're using this and you accidentally kick the wire, okay, it's going to stop the cable being pulled out and allow it to be safe to use. Okay, so it's going to stop you kicking the cable out and stop you pulling the wires out and exposing the live wire. Right, let's go through the wires now then. So we'll start with the live wire. So this is at 230 volts. Okay, now I'm not going to write these things because you can see them on the picture, but it is brown. Okay, bit silly, but the way I remember this is a live wire is brown because that's what colour it makes your trousers go if you touch it, because it's very dangerous. Okay, take from that what you will. So live wire, touch it, it's going to hurt you because it's at 230 volts. You are at 0 volts because you stood on the floor. That's a potential difference of 230 volts, which is enough to send electrons through your heart and cause some damage. So live wire carries 230 volts to the appliance. So from the plug to the appliance carries 230 volts. Your neutral wire is at 0 volts. Okay, I mean it's not dangerous because it could, if it's part of the circuit, you're getting some current flowing back through it, which can be really dangerous still. So you don't want to touch it. But it's at 0 volts, and that's so that there is a potential difference from the live to the neutral of 230 volts, which should be, if everything's working right, everything's okay, it should be going through your toaster or your hairdryer or whatever, and causing things to actually work and do stuff that you want it to do. Right, now to our 2 safety features. So we'll do the fuse first. The fuse melts when current gets too high. So if your current gets too high, your fuse will start to glow red, okay, and eventually it will melt. and when it melts, it breaks the circuit and stops the circuit, breaks the circuit and stops everything from happening. Now your earth wire, okay, is connected to the metal outer casing. Okay, so it's connected to the metal outer casing of an appliance, and if something goes wrong, the current will go through the earth wire instead of going through you as someone who touches it. Now, when that happens, it links with the fuse. So basically, the fuse is connected to the earth wire is connected to the metal outer casing. So if the live wire breaks and touches it, so you've got a metal toaster, your live wire inside your toaster is broken, touch the casing, that's live. And if you touched it, you hurt yourself. But before you can even have a chance to touch it, the earth wire carries the current straight to the ground. Now when that happens, the earth wire is a big thick piece of wire, whereas your toaster's got lots of little bits inside it which have got high resistance. So we've got a very low resistance, and we've already said that low resistance means high current. So we've broken your live wire, the current's going now, instead of going through the casing, going through your earth wire, which means it's a very low resistance and high current. And the high current causes your fuse to melt, which switches it off for good, stops everything from breaking, and it stops anyone from getting hurt. Okay, so two safety features working in tandem, working together to prevent people from getting hurt. Right, last bit then. So the national grid. So first off, you need to know what the national grid is. So it's a system of cables and transformers that connect power stations to consumers. So when we're looking at this picture, we're looking for a system of cables and transformers connecting power stations to consumers. So that means it's not it doesn't say including power stations and consumers, it says connecting. So the bit that's actually the national grid on here is these three in the middle. We've got step up transformers, step down transformers, and the high voltage transmission lines. Now there's a few things you need to remember for these, mostly about the transformers to be fair. The high voltage transmission cables, just really quickly, they have a very low resistance to allow as much current to go through as possible. Now we just talked about with the fuse that when the current gets too high, the fuse melts. Okay, that's because high current causes high temperatures. Same with the bulb we looked at before. As the voltage went up, the current went up, and then it got really hot, the ion started vibrating, and it started to cause a high resistance. We don't want that. Okay, we want to have as low a current as possible going through these wires, because the less current there is, the less heat there's going to be given off, and then it's going to be more efficient because you're not wasting energy. So what the step-up transformer does is, okay, make it a bit smaller, it increases the potential difference, which decreases the current. So less heat is lost and it's more efficient. Okay, so that is our step-up transformer. That's what the step-up transformer does. But so what we do, it comes out of the power station. It comes out of the power station at about, I'll put the voltages on here, the potential differences, sorry, on here. So it's about 20,000 volts. It's not always, okay, it changes depending on what type of power station it is, depending on lots of different things. But we'll just say for this example, that's 20,000 volts. Our step-up transformer steps it up to about, let's say, 150,000 volts. Again, some might be up to 400,000 volts, some might be even higher than that, some might be a bit lower depending on how far it's got to go. So basically, rule of thumb, further it's got to go, higher your potential difference you need, because you want to waste as little energy as possible. So 150,000 volts rushing through our high transmission cables, okay, high voltage transmission lines, sorry. Really low energy loss, okay, really low energy loss because it's such low current but such high potential difference that you're not losing much energy. Right, great, so let's just shut that into our homes. Apart from that would be very, very dangerous. So what we need to do is have a step down transformer, and in the step down transformer, basically pretty much the opposite happens. So we decrease potential difference, okay, which causes us to increase the current, and that makes it safe to use. And when we decrease the current, we decrease it to the standard British potential difference that we use in our homes, which is 230 volts. Okay, and just because I've not said it anywhere else, it should be 50 hertz. That's the frequency. So that's when the current is changing directions, because it's alternating current, which means it's changing directions. It's changing 50 times a second. Okay, so 230 volts and 50 hertz. Okay. Right, that should be it. So you should have everything you need, hopefully, with this, as well as you should have been given out some vision guide pages to work your way through the electricity section of your work for this week. Okay, thank you for watching.